Hello gentlemen, welcome back. Last video on rational functions. Basically all we're going to do is a couple examples and hopefully put everything into place for you guys. So let's get started. Now let's look at graphing this function right here, 3x to the fourth plus 2 over x minus 1. Okay, and let's go through our steps that we need to do in order to graph this function. First and foremost, interested in domain. Okay, domain is for rational function. We're looking at when is the denominator equal to 0, and if it is going to be 0, then that's going to restrict our domain. In this specific example, you should see that the domain is all real numbers except for 1, because when I plug 1 in, I have a 0 in the denominator. We know we can't have that. Okay, and so then we have to decide, do we have any vertical asymptotes? Well, because I can't factor this out and cancel this term, I'm going to have a vertical asymptote at x equals 1. Okay? So I'm going to have a vertical asymptote at x equals 1. Remember, if I could cancel it out, if, for example, if I had this right here, this function was 3x to the fourth plus 2 times x minus 1 all over x minus 1, if that was my domain, if that was my function, then my domain would still be all real numbers except for 1, because I can't plug in 1, I get 0 in the denominator. But I wouldn't have a vertical asymptote anymore, because I could cancel that, and I would end up with just the whole. Okay? But that's not the situation here. The situation here is we weren't able to cancel that. So let me get rid of all this, and let's continue on. Okay. So once we know we have a vertical asymptote, we need to determine what the behavior is going to be. And so we want to take the limit. We're going to look at the behavior to the left and right of 1. And so again, remember, when we're coming in from the left of 1, so we already know we have a vertical asymptote at 1. Okay, if I'm coming in from this side, the left, so that means I'm getting a number a little bit smaller than 1. So let's say when we're coming in to the left, we're going to say 0.09999. Actually, this is 9. A bunch of 9s. We're getting really close to 1, but we're not quite there. Top is always going to be positive because it's an even term, even degree. And so I'm going to take that and I'm going to divide it by a really small, and down here is going to be negative because x is a little bit smaller than 1. Minus 1 is going to give me a small negative number. Okay, so something like negative 0.000001, etc. And that, you should understand, is going to approach negative infinity. Okay? Now when we come in from the other side, I'm going to come in from the right over here. Now I'm going to get a number like 1.00001, something like that. This bottom term is going to be positive, so I'm going to have a positive number divided by a really small positive number. So this top is actually going to approach 5, because when I plug in 1, 5 divided by a really small positive number is going to send this off to positive infinity. Okay? Let's look at, are there any real zeros? The answer here is no, because the top can never equal 0. All right? You can't have this. Well, I'd end up with 3x to the fourth equals negative 2, or x to the fourth equals negative 2/3, and I know I can't have an even root of a negative number and get a real solution. Okay, my solutions here would be of complex nature. Determine the end behavior. Again, what's happening when x is approaching infinity? Well, as x approaches infinity, look at the degree on the top and the bottom. Degree is 4, degree is 1 here, right? Because the degree in the numerator is greater than the degree in the denominator, this is going to go off to infinity here. Okay, because this is going to be positive, this is going to be positive. The x to the fourth is going to grow much faster than x in the bottom. So that's going to go off to infinity. Let's look at what happens when I go to negative infinity. Again, this term is going to grow much more quickly than this term, but note the top is going to be positive because I'm taking a negative number and I'm raising it to the fourth power, makes it positive. The bottom is negative, so I got a positive number divided by a negative number. So this is actually going to go off to negative infinity. Okay? Last thing we want to know is what's my y-intercept. So I plug in x equals 0 and I get negative 2. Okay, so now I have all the bits of information. Let's put it all together. Here's my vertical asymptote at x equals 1. We said as we came in from the right, we went off to positive infinity. When we came in from the left, we went to negative infinity. We said that there were no zeros, so you never see us intersect the x-axis. We had y-intercept of negative at 0, 2. And we also note the end behavior. As x grew really big, this function goes off to positive infinity. As x headed off to negative infinity, the function also went to negative infinity. Okay? Let's do a word problem here. Game Commissions introduces 100 deer into a newly acquired state game lands. Okay? Population is given by this function here, where t is greater than 0, where t is the time in years. I want to graph the function and determine the limiting size of the herd. In other words, limiting size, I'm thinking about, what you should think about is a horizontal asymptote. Okay? And we'll see what that looks like here in a minute. So let's go through the process again. Process states, what is the domain? Here it's going to be all real numbers because t was already required to be greater than 0. If t is greater than or equal to 0, there's no way to make the denominator 0. Okay? So all we have to satisfy is t is greater than 0, which should make sense to you. There are no vertical asymptotes. Well, if I don't have a situation where my denominator is going to be 0 on the domain, therefore we're not going to have any vertical asymptotes. Okay? There are no zeros on the domain. Okay? And the reason is, on our domain, if I wanted to solve the zeros, I would look at when is the numerator 0. If I look at 60t plus 100 is equal to 0, that would be 60t equals negative 100, or t is equal to negative 100 over 60. Well, my domain is t greater than or equal to 0. Obviously, that's not in my domain. And to get my y-intercept, I would have n at 0 is 100, and that's the information that I'm given right there. I could also plug in 0 right there and get 100. So what's the end behavior going to look like? Well, in this particular problem, I need to know what happens when t goes off to infinity. I don't have to worry about negative infinity here again because that's not in our domain. So as I look at this, I look at my leading, I look at my degree in the numerator and denominator. The degrees are the same. They're both 1. And because they're both 1, we need to look at the ratio of their coefficients. So this limit is actually going to be the ratio of the two leading coefficients, which is 60 and 0.04. And if I look at that ratio, I'm going to get 1500. And so what my graph looks like is this. I'm going to start down here at 100. I'm going to increase, and I'm going to approach this horizontal asymptote of 1500. Okay, I'm going to get closer and closer to 1500. Never going to get there. Okay, and so my limiting size, the biggest the size is going to be for this herd is 1500 deer. Okay. Here's some more practice, fellas. Look at these couple examples, couple word problems in there, some more practice problems. I know that this section had a lot of information on it. Hopefully you guys are getting the hang of it. You're understanding about the domain and when we have a vertical asymptote and when we have a hole, and how to find horizontal asymptotes. The steps are always the same. The application, we're going to get some different results, but you should know how to interpret them. Okay? Again, questions, make sure you're emailing me, and we got one more section to go, and then we'll be in good shape. All right, fellas, have a good day.